Let me start. Let me continue where we stopped before, a little bit. And so in this last time, I will continue a little bit more about the shape memory model development, and then I will speak briefly about the technology to make nitinol textiles. So if we currently for last maybe how much? Maybe 4 years during the COVID, we couldn't go much to the conferences. I have been working a lot on this research focused on understanding of the plastic deformation of martensite. Why? Because we found in TEM, in analysis of TEM, this kind of deformation bands, and we realized that even the plastic deformation of martensite is due to sort of twinning. You know, if you have, as I said, the martensitic transformation proceeds by nucleation and motion of interfaces. The plastic deformation of martensite, based on the results of this TEM experiments, also proceeds by nucleation and propagation of interfaces. It's not interface between austenite and martensite, but it is interface between martensite and martensite, intermartensitic interface. And and realizing this, there is a good chance to develop some model which would capture this process, and this plastic deformation is very different from the plastic deformation which proceeds by dislocation slip. But and these people who develop the models, we collaborate together, we try to design different experiments and try to think how to include this mechanism into the model. So when I proposed this topic, it was 2 years ago, I hoped we already be in the model will already be here. The model is not here. We are in the middle because we found new and new phenomena by doing these experiments, and then still, but I will try to introduce the basic principles how the plastic deformation is introduced into that model. So before I already showed this diagram, but there was not this one. So as I said, that this is only due to the deformation mechanisms which are derived from martensitic transformation. So only the transformation and twinning. But during the week when I shown different kind of experimental results, it was clear that the plastic deformation can occur during, you remember yesterday, lots of this, if the transformation proceeds at high stress, there is a lots of plastic deformation. If we continue here, there is a yielding, and here the plastic deformation proceeds. So we somehow, even in the modeling, we cannot stay only with this shape memory models which are limited to martensitic transformation only, but we have to think how to include the plastic deformation. We are not the only one who do it. There is, you will find some groups who already entered into this field by different kind of approaches. One is just to include plasticity, like in plastic deformation model. The other is to include TRIP, transformation-induced plasticity, which is plasticity which proceeds alongside the transformation. But this is in steels. TRIP steels are very famous. But in TRIP steels, you have transformation and plasticity like going side by side, but in different place. But in shape memory alloy, as I have shown, the part of the crystal which transforms to martensite is the one which deforms plastically. So we don't have really trip. So you cannot take directly the trip equation and put them into the shape memory model because the mechanisms are very different. Even though both is about simultaneous transformation and plasticity. Now, so this is kind of summary. The plastic deformation could be at very, very high stresses applied at any temperature, but so if you at high stresses and high strain, so if you deform beyond this yield limit, you will get plasticity. But if the transformation proceeds at high temperature, means at high stresses, you will have the plasticity also already during the transformation. So it will be unrecoverable here. So this is something which should be captured, so appears during mechanical loads at high temperatures. And there is another like a principal point. If I have a shape memory alloy element, and if it deforms only by martensitic transformation, I do any kind of thermomechanical closed loop, and if I come to the same point, I am in austenite and there are no defects. I shown in this shape memory effect yesterday, we load in martensite, unload heat, and there are no defects inside. So these models assume that the shape memory closed loop cycle will be completely closed, no unrecovered strain, no defects. But if I have simultaneous plasticity, so I make the closed loop cycles, there will be unrecovered strain, so some plastic strain will remain, but also the sample will change because you will have these dislocations inside. And the sample without dislocation and with dislocation is different sample. It can have, so now I need a model for different sample because my material parameters are changing. So there is a problem how to capture this kind of, I would call it microstructure evolution, which is connected with plasticity, and this is irrecoverable. This is here until you heat it to 500 Celsius. It will stay here and it will accumulate. And it can tremendously, I mean, the microstructure which could be created by that plasticity could be very, very important, and it will change the behavior from this type to this type. So it will affect very significantly. So we have the problem that your material is it introduces the strain heterogeneity. This is the change of the microstructure of austenitic microstructure, and then your sample is evolving during the cycling, and the model have to somehow capture this one. So the models which you find in the literature try to deal with those problems, and so it is shown here. Also, I mean, if you are here up to this stress, you are safe. You should be in the transformation range, but behind the yield limit, your microstructure is changing. There are the twins inside, dislocations inside, and so your sample will change. And here, if you cycle even at room temperature on soft material, you start with such kind of material, and after 10,000 cycles, you end up with such kind of response. And this is also because of the change of your specimen. It's not, you cannot simulate this with the shape memory model, which doesn't have any plasticity, because this would require stable performance. It would have to be stable, but this is unstable, and this unrecovered strain is connected with microstructure in the sample with many dislocations and twins and so on.
How much time is this experiment to take it to 10,400 cycles?
10,000 cycles? You want me to calculate it now? I don't remember. 10,000 cycles, one hour, 2 hours typically, because we use low strain rate to avoid the problem with this adiabasity. So like one cycle 1 minute, no, so 10,000 minutes. Yeah, but important is like the hysteresis. Yeah, so I mean hysteresis. In many models you will find for nitinol that 200 megapascal is the hysteresis, which they put like material parameter. But after 10 cycles, it's only 50 megapascal. Yeah, and why is that? Because with plastic deformation, the microstructure of austenite evolves, so the material parameters also evolves, so the hysteresis is different after 10,000 cycles. Okay, and so this is, I said that you have the problems with plastic deformation at high temperatures and high stresses. So this is the set of stress strain curves until fracture on nitinol shape memory wire, which we have used in the demonstration over here. So yesterday when we looked on it was at room temperature like this green one. So you see the green curve. This is the curve which we approximately measured yesterday in the laboratory test. So there is a reorientation, it's some kind of around 6%, and then around 1 gigapascal there is a flow. Exactly yesterday in the test we had the plastic flow and at 1 gigapascal. So if you see here, this is at minus 100 Celsius, and this is at room temperature, so 100 Celsius difference, and the curve, this slope here is about the same. Yeah? So at low temperature, the characteristics of the martensite, at low temperatures there is no plasticity, everything is fine, so you will get only here, this is the reorientation plateau. It doesn't depend much on the temperature, so between 75 and this is minus 20, also like 50 degrees, it's decreasing. Yeah. So at lowest temperature it is almost 300, minus 60 degrees like 200, and you come like 160 at room temperature and 75 degrees. So the plateau, yeah. But look here, yeah, this depends on the, so when we deal with this plasticity, we also use the stress temperature diagrams, but now in addition to the transformation line, we put here the line for reorientation. This is the reorientation. We put the line for plastic flip, which is the change of this yield point with temperature. Also, we change the temperature, and the yield stress is changing from black to cyan somewhere along this line. Yeah, and okay, so this is at low temperatures. But when we go to 100 Celsius, suddenly you see that this slope becomes different. It becomes different, and so to make it more clear, when we continue to higher temperatures, I start again with 100, but just a little bit different, 115, 115. You see this slope here is like this. So what's happening? Why is that? No, this is because at high temperature some plastic deformation already proceeds in. Here it was elastic only. But at high temperatures, because of somehow the martensite start to deform plastically, and you will get this change. But this flow, this plastic deformation range will be about at similar stresses, around 800 megapascal. Still, you will climb out to this level. But you have the change here, and also you have the change here. So here you have austenite to martensite transformation. Here also 115, but 135 you already do not have the plateau, and here you have it like this. So how this can be understood? You know? I need you to understand what is happening with the wire if you deform it at high temperature, because this is the topic of including the plastic deformation. So, in fact, here the austenite transforms to martensite, but when you go to 115 and 135, together with the transformation, you will have already some plasticity. Or, because I said that the martensite is the softer phase, what we now believe is that inside the material, when the martensite is induced, it's like a plate which is in the grain, it will immediately start to deform plastically. Yeah, so because the martensite is softer than the austenite, it is induced by the stress, because the stress for inducing the transformation is quite low. The austenite is not deforming plastically, but martensite is deforming plastically. And so we end up with a curve like 150, and then from 150 to 300, which is here, from 150 to something like 300, I have, the curves are sort of similar. You know, 150, 200, 250, and then at 300, suddenly, instead of plateau here, this goes down. You have some kind of unloading, softening during the deformation. And if we continue at still higher temperatures, 300, 350, 400, you see that this softening is kind of same slope, independent on the temperature. So, well, this softening, we know this is already typical for dislocation slip in B2 material, and so we have here this line, which is the stress for slip in the austenite. So if you look on this diagram, in this diagram you have here this is the stress for inducing the transformation. So here there is like you are in martensite state, and then between 150 and 300, this is here between 150 and 300, you have some kind of transition range where I said the martensite which is induced immediately deforms plastically. Yeah. So if we have this diagram, we can now like try to understand the behavior of the wire from -100 to +400. So we can cover both transformation and plasticity. This was published in very recent article, which is actually about something different, which is about you see here there are points which are fill and solid. Yeah. So I think solid is R from this experiment, and these are from the experiments where we cooled the wire, loaded it to maybe 900 megapascal, and then we are heating it. So what happens when we are heating the wire under the constant stress? Any idea what will happen? There could be creep, but because we are cooling with some rate, we don't measure much creep. And I tested the creep, and there is creep, but not very much pronounced. But simply, okay, this would be new for any shape memory people. Like, you know, here transferring this line is here when you are loading, so the plastic deformation starts. Okay, and this process which is occurring here during loading at constant temperature, which is like a plastic yield stress, and it here proceeds at constant stress. It can be initiated also by heating under constant stress. So even if you are at very, very low temperatures, by heating the wire under constant stress, it will start to deform plastically up to 60%. And okay, this would not be surprising if you have like thermal activation at high temperatures. This is sort of acceptable. But understanding why it happens at minus 100 Celsius. There is no thermal activation, and there should not be any thermal activation. So we have now in this article, there is this process of thermal activation described. But in order to understand it, we needed this diagram and we needed these kind of curves, no? AF temperature here is like 90 degrees, measured from here, from thermal cycling under low constant stress. It's a memory wire. It's the memory wire. Yeah, okay, here at around this curve at 100, which is here, it would be superelastic, but slightly more, 115, if you try to make superelastic, it will end up, there will be some unrecovered strain. It's a good question. You have superelastic wire, which is superelastic at room temperature, and you have memory wire, which is martensitic at room temperature. Which one will be easier to observe superelasticity around 120? In memory wire or in the superelastic wire?
Memory wire.
Why?
Because thermodynamically we are very close to air.
Yes, very correct answer. Because in memory wire you are thermodynamically close to AF or T0, so the stress will be lower. And because the stress is lower, these plastic deformation processes will not occur. So you can observe on shape memory wire, you can observe superelasticity at 100 Celsius or 120. But on superelastic wire, if you heat it to 100 Celsius, the stress is like 600 megapascal, lots of martensite deforms plastically, and it's irrecoverable. So this is the reason for developing the high temperature shape memory alloys, because they have higher AF temperature, and we can have superelasticity at 200, for example. So this is very, very nice. One interesting point, when we deformed the some postdoc was working on it. It's a lady from Russia, and so she used the DMA to measure these kind of curves. And when she used the DMA, these curves at maybe 400 Celsius, they look like it started here, and then it was flat, and then it fractures. So it was completely different in DMA. In DMA, you use the force control. You prescribe the force. So do you understand why it was different? No, because this is not, here, the material deforms by dislocation slip. And dislocation slip is rate dependent. And when she used the force control, it deformed, and then very quickly, because she prescribed the same force rate and high, and if you use high strain rate or high force rate, the stresses are higher because of the strain rate dependence. So the faster you deform, the higher is the stress. So it was kind of, I didn't understand why is that. So then we remeasured it again in position control, and when in position control we got such kind of responses. So yes.
In the last this 400 degrees Celsius one. What will be YS and UTS? Will it be same or will it be different?
Well, UTS here. This is actually this line, So it decreases because of thermal activation, basically. This is common for any dislocation slip deformed material. You have with increasing temperature, the UTS is decreasing.
How do we make plasticity models for this kind of a curve which declines after UTS. Straight softening will do the work, basically.
The stress softening is this, and it shows that the strength softening is independent on temperature. Yeah. So this is something which you can put into the model. And then you have experimental evidence for this decrease of UTS. So this is here. And that's all what you need to model the plastic deformation. Yeah, but we don't bother much with that. We only include it into the scheme so we understand what's going on in the wire. But very nicely here you can see this kind of transition. Because there is this line and then this line, but there is nothing here. So around 200 degrees C and 250, I don't really know. And this is here, and so 200 and 250, these two lines where the transformation occurs together with the dislocation slip. We don't really understand what's going on in the wire. There is no lines. Yeah, so it's difficult to understand.
Graph, yeah, this T, you said at 400 degrees Celsius this curve. So that was done in DMA.
No, this was done in meter after. When I realized that DMA can use only force control, so I said do it again with meter in the strain control, and so you have to. This is like one has to be careful. If people using DMA for thermomechanical testing, the DMA works in the force control, and for material which are strain rate dependent, this is critical, and frequently,
So in the first diagram, right, there's something about the 6% strain in the first one, top left. Yeah, the bottom, yeah, 6% strain. At the bottom, yeah. What happens to that small little region?
Well, this is from -200 to plus maybe plus 70. Yeah? So in this range, the material is in the martensite. So here, this represents the reorientation of martensite. This is on this line. When you cross this line, the martensite reorients. So at very low temperature, the stress is like 300. Around 70 degrees, the stress is like 100. This is the decrease from here to here. Yeah. Okay. Well, so I would start from this one. So in the model which I talked before, which was only for phenomena derived from martensitic transformation, so I have two phases. There is a martensitic transformation between them, but in addition, there are processes inside the austenite. So inside the austenite, it is only elastic deformation, nothing else. It can deform elastically or to transform to martensite. In the martensite, you have elastic deformation, but you have also these variants. So you have reorientation. Reorientation means deformation mechanism inside the martensite. And so for this, we have here the model already developed, but now when we want to include plasticity, we have to update this. So in the austenite we have elastically deformation, but we can have plastic deformation, which we have seen before, this high temperature behavior. This was plastic deformation of austenite. You remember the green here, there was the green line. This was plastic deformation of austenite. So we have to have this, and in the martensite we have elastic deformation, we have reorientation, and plus we have some deformation in the martensite. So this was included into the model, and we kind of try to simulate the experiment, because always the way how this modeling is done, that you introduce new feature and then you use the model to simulate something. You know? So the very first thing you want to simulate is this Clausius-Clapeyron line. So this is stress temperature, and this is the experimentally determined diagram. So if it's shape memory only, this is the Clausius-Clapeyron line, and it should go forever until the fracture. But these are the real points which are measured in the experiment. So, and now I am again in this range of 150, 200, where both transformation and plasticity occurs. So the model kind of tries to include this into the equation, which is shown here by adding the plasticity term and reorientation term. Now, well, as I said, we are working on it, but it's not completely developed. And one of the problem is the understanding of this recovery stress behavior, which occurs when you are heating beyond some maximum temperature. So this is the experiment when the wire is stretched, fixed, and heated. But upon heating, now I don't stop here and don't cool, but I continue heating up to high temperatures. And when we do that, we see the maximum of stress and the increase. So we are fighting with understanding this phenomenon, because what does it mean? This means that I have a wire. The wire is completely martensitic. I am heating it. The stress is increasing. And at constant length of the wire, this martensite is transforming to the austenite. And wire is constant. So wire length is constant. So it means that the elastic strain is constant. So if the stress is increasing, the transformation strain goes to the elastic strain. But stress is not increasing. Stress stop increasing and reach maximum and start to decrease. So the only possibility is that this oriented martensite is transformed to the austenite without going back. So we have to understand the mechanism how this oriented martensite transforms to the austenite. I need to show some experimental results to explain that. So I will continue on that furtherwards. But basically, here is described some kind of internal variable which simulates this kind of behavior. But for me now it's difficult to talk about it if I don't explain the mechanism. But simply you can understand these schemes like that. When you are loading this wire, the martensite is transforming to the austenite, but at the same time it is changing the microstructure. And indeed, in this maximum, the wire austenitic microstructure is completely different, with many introduced defects inside, and we are attempting somehow to introduce this into the model. I will come back to it after explaining the experimental evidence for something like that. Okay, what are the experiments which are behind this? Yeah? So, for example, this is shown here. So this is temperature, this is strain. So we heat the wire, again the same thing. Yeah, we heat the wire into the austenite, then load it by small force, and then not small. It's pretty high. It's in fact then load it up to 1100 megapascal here. So this is elastical loading in austenite up to 1100 megapascal, and then we are cooling, and when the transformation line is reached, it transforms into the martensite, and when you are heating, normally the transformation would go back. But because the stress is very high, it constants like this. Upon next cooling, you will get like 25%, upon like 22%, upon next cooling 25%. So you have such kind of ratcheting because of the plastic deformation. So this is something which is completely out of, it never happens in shape memory alloy when it is loaded at small stresses. But when we want to include plasticity, we have to be able to simulate such kind of tests. No. Well, I probably will not go now to the details of this because it's too early. This is just the figure we published very recently about the evidence for this deformation mechanism inside the martensite. So when we look, this is okay. This is about this line. So when we deform and cross the yield point, the martensite deform plastically, and I discussed here that even upon cooling under stress it will deform plastically. And when we look into the microstructure, we see such kind of microstructures where here there are individual deformation bands, and depending on the orientation they are now painted. So there is such kind of microstructure. So the blue was the matrix. This is the orientation of the martensite in the matrix, and all those kind of bands, they were introduced by the deformation. And there are some specific features of this microstructure, and one of these features is that if we orient this stem lamella in such a way that it is O10 direction is aligned with electron beam, we find out that this grain becomes completely black. I shown you before. So what does it mean? This means that all these variants, this is the oriented martensite lattice, is oriented in such a way that O direction is here, and it's only rotated in this direction. Understand? Yeah. So, here the out of plane direction in all variants is O10. So when we look on it in O10 and all interfaces are, this is the electron beam, and all interfaces are aligned with the electron beam. So we can go even to high resolution mode, into the high resolution mode, and we can look how the martensite lattice is organized along the interfaces. And if you see here, you see some lattice planes. So for example, this is this compound twin, and here you see the lattice planes, and the lattice plane here is parallel because this is the characteristic of the compound twin. But then there are other twins which are in this microstructure, and what is interesting is that if this is the trace of the O01 plane, and this is the interface, you will find that there is a mirror symmetry across this interface. But okay, here it is not surprising because the lattice is mirror symmetric across this interface. Another twin is here, which is 2O-1 twin. Again, it is mirror symmetric against this plane. But any other interface which I have here, you will find there is a mirror symmetry of O01 planes. The angles could be different, but in each case there is a mirror symmetry. And now these are sort of other general interfaces where even the interface plane in left grain and right grain could be different, but still I have here such kind of mirror symmetry. So when I have seen it for the first time, I was sort of shocked. What does it mean? It was not understandable at all for us, you know. But then we continue to work along this along this direction, and we came to a sort of very logical explanation. So these interfaces which you have seen before, they were created by plastic deformation. So plastic deformation can proceed by twinning, and this is now in the field generally known. So this 2O-1 twin, this is a twin which can be created by deformation twinning. It has been observed in nitinol, and there is some theory in the literature how this deformation twinning proceeds here. Of this theory, which is published in the literature, they assume some shear and shuffle, and the energy which is necessary for such kind of atomic displacement at low temperatures is very high, and somehow many people claim this is unrealistic, it cannot occur. But we observe the twin, so it must occur. So if there is a geometrical theory which explains how such twin is created, it is here for last 10 years. Everybody believes that the twinning proceeds. But on the other hand, we have this information, and we see this is 2O-1 twin, so this is this twin, but in addition to this twin, I have this one twin and this twin, which is completely different, and what is the same is only mirror symmetry of 001 plane. Okay, and then I should say this is a martensite which is monoclinic, and monoclinic lattice is very anisotropic in a sense that the only dislocation slip which can occur is in this basal plane 001 in 100 direction. There is no other way how it can deform by dislocation slip, and this is common to some geological materials which are also low symmetry materials. And in geological materials, we know from the literature the way how the material deforms plastically is via king bands. King bands are so-called bands of coordinated dislocation slip. They look like twins, but inside the lattice is slipped in a coordinated manner. This occurs because of the extreme anisotropy. So taking the lesson from those geological materials, we kind of suspected that it is possible that that actually this 2O-1 twin can form by combination of twinning and slip. So the twinning will, there would be twin, which means that there will be a particle which goes through the material, but the narrow twin which is here will immediately deform plastically by dislocation slip. This is possible. This is what happens in these geological materials. So what we will have is this is suggested in this scheme. So this is the austenite. This is the single variant which is created by stress. So it is longer in this direction, okay? And then I can have, so this is the variant which produces maximum strain. So no twinning, no further twinning can make it longer. Every twinning which you would consider will make it shorter, okay? But I can assume that the crystal, this yellow crystal, will undergo this twinning, and this twin will immediately deform plastically. So when these two things occur together, I get elongation. Okay? So this process will this process will create this is matrix, so this process will create a twin, and at the same time it will immediately slip, so it will create a band which would look like a twin band, but it's not created by twinning, but via combination of twinning and slip. And it is no, I mean, for these geomaterials, this kinking is widely accepted, and they don't see any dislocation. They see just the bands, and this theory describes very well the creation of the kink. So, well, here, if you look at it, I mean, the twinning, this type of twinning give always shortening. So there is no way how the twin can further deform this material. According to this scheme, the only way how to deform this material further is this combination which we call twinning and kinking, so we call it quinking, and it produces the expansion. I mean, you can do the same thing even without the twinning, then it would be just some plane and quinking. But there is one very important thing. If the material deforms and creates the internal interfaces, this interface must be strain compatible. So in case of twinning in martensite, this strain compatibility, this is a basis of mathematical description of properties in martensite. They call it so what we do we like because now here the strain which is here is a combination of twinning and dislocation kinking, which is a dislocation based process. So we don't have a limited set of finite strains because we can add this dislocation slip. And when we do this, when we do this, we can nicely reconstruct all these type of interfaces, and this condition on the strain compatibility now in our case would mean that the strains on both sides of the interface are the same. And because the strains on the sides of the interface are shears along this plane in this direction, and here I have shear along this plane in this direction, the compatibility means that this will be a mirror symmetry. So it explains the observation which I was so surprised and how it can be that there is such kind of mirror symmetry. So the condition is that then doesn't have to be a mirror symmetry of the lattices. There is no mirror symmetry of the lattices. There is mirror symmetry of shears, which is recorded as mirror symmetry of the traces of 001 planes. So we claim that we are now at the level of possible understanding of this mechanism. So we have to reconsider the way how the model is implemented, because this means something. This has to be included in the model. This hasn't been yet done. This is the explanation because this is critical of this. What is it that king band? There is a article in the literature which is cited in our papers, and this is very nice. The guy put together a stack of 200 papers on itself, and then he deformed it, I think in compression like this. But because these papers, they can very easily glide along this direction, but the other deformation, there is no way how to deform if you compress. But what the material will do, even though the shear stress into this shear is zero, it will start to generate such kind of pattern which you can observe if you look by the microscope on the side of this stack of the papers. And this is exactly what happens into geomaterials. So you see such kind of bands, and these are basically the bands which we see in the TEM, and where these along these interfaces the strain is compatible. So like philosophically it is very interesting because we have martensite. It creates the twin bands. So the people, we believe it deforms by twinning, but the twin bands are created by coordinated dislocation slip. So in fact it is a dislocation mechanism. It's not twinning. It's dislocation mechanism only here inside these bands you have a coordinated dislocation slip. Coordinated means that in order to create a shear, homogeneous shear in this stack of papers, you have to guide on every plane some shear. So in this way you get the king band. And so this has a deep consequences. For example, because it is a dislocation mechanism. So if I want to like strengthen the material for if I want to increase this yield stress, so I have to do something to prevent the dislocation to move. So what I can do? Well, make the grain size smaller. Smaller, this is very good stuff. So smaller grain size, higher yield stress. I can, if I decrease the temperature, because slip is thermally activated, I will have higher yield stress. You remember there was this diagram and the line here had this slope. So it explains the slope. If I do precipitation, if I heat treat the material at 300 degrees C for 1 day, I introduce nano-sized precipitates, they will block the dislocation motion, they will block this mechanism. So suddenly the things which were obscured become clear. And all this have to be introduced into the model in some suitable mathematical form that it can be used for treating general problems. Yeah.
2 slides. Yeah. What is the difference between this quick and low angle grain boundary?
Okay. Well, first thing is okay. Quink is our term for a deformation band with where the lattice is oriented differently than in the matrix. So in this case, this is not low angle grain boundary. There is a very big misorientation. But I can have such band where there is only slight rotation. This kink could be only slight rotation. I will still get the kink. Actually, it's I guess. Yeah, here, you see, this is the matrix. This is only slightly oriented, but there is a very nice interface. Yeah, but the change of the angle is only 7 degrees. So this is low angle grain boundary. So in this case, this is not quink, this is kink because this lattice here. Okay, here these are two lattices denoted by these two prisms, and this is only rotated. If I rotate the blue, I will get the magenta. So the lattice is only rotated. This is kink, but it creates a very band which can be nicely seen in the diagram. And the band is on 100 plane approximately. So it's 100 kink. But in this case, this is not low angle grain boundary, this is very high angle. Yeah? The beauty is that these twins are created by dislocation slip. This is what I like on it. You know? If you have coordinated dislocation slip, you form bands which are very similar to twinning, and so we know the deformation mechanism which creates them, and because they are not twins, we come with a different name, quink. Quink is a combination of king and twin. K from one and W from another one.
Sir, adding to that, kink band, it is limited to only very limited number of planes, interatomic planes, maybe 5 or 10, not more than 15. Whereas grain boundary, low angle grain boundary, it extends up to a micron level, sir.
Well, okay, if you say low grain boundary, it
extends up to a very long.
Okay, if you look here, no way there is a single boundary. There is always a band and two boundaries around. This is the characteristic of the twin. You have matrix and thin plate in between, which is a mechanical twin. I mean, many materials deformed by mechanical twinning, magnesium, titanium. Yeah. So this is always two parallel interfaces. Yeah. So when we speak about kink bands or twin bands, we always have two parallel interfaces and plate between them, just like it is shown here or here. Yeah. And your question was?
I was adding to that what is the difference between kink band and a low angle grain boundary. The kink band is limited to very few number of interatomic planes.
Now, you combine now 3 or 4 things together. Yeah? So first thing is, okay, here this is 10 nanometers, so this band is only 10 nanometer thick. So you will not see it in optical microscope or SEM. It will not be visible. It's visible only in TEM. So you are right, it's only few nanometers. The question is why it is only 10 nanometers, why it's not brighter. There is no meaning to compare it with low angle grain boundary, because low angle boundary concern a single interface which is created during the growth of the crystal, for example. So you have like a crystal with many dislocations, aluminum, you heat it, and this dislocation annihilate, and they will create, because of the energy is minimized by forming the low energy grain boundary. So yeah, lattices are rotated across the low energy grain boundary and it's coherent. So the difference is that typically these boundaries are created by diffusion when the dislocation defects disappear into the boundary. Basically you have defects everywhere and they go to the boundary and align and make low angle grain boundary, while here the process is completely different. You have temperature is -100 and you are plastically deforming the material, and these interfaces are created by coordinated dislocation slip at low temperatures. So I wouldn't compare these two things together. You know, they are different things. But geometrically, you may call this low angle grain boundary. You can describe it as the stack of dislocations. It is a low angle grain boundary. But the way how it was created is completely different than commonly known in the literature.
Since from the last 2 decades, people are using plasticity models in a finite deformation sector. So is there any specific reason why you are following a small deformation?
Yes, that's the thing. You know. So now I said that okay, here if we use twinning, so we can characterize this twin by a finite deformation gradient, you know? And these deformation gradients for each alloy, they are known, they depend on the type of the martensitic transformation, and they will tell us that if this twinning occurs in the material, I would have I would see them, and the strain would be compatible here, but this is a single deformation mechanism, and if you imagine the grain, if there is only one deformation mechanism like this, it would be very difficult to deform by only one deformation mechanism. Yeah, so that's why in the materials like magnesium, you always have deformation twinning and dislocation slip together. So you have deformation twinning and the lattice around deformed by slip. The same with trip in the steels. You have transformation and slip as ever. In this case, in our case, it is different. We don't have slip as ever because the material is such anisotropic, like this stack of sheets. But we have the slip inside the band. Yeah, so we have the slip. It is slip mediated, but it forms bands, and this microstructure, because the bands are formed by slip, is strain compatible. Every interface is strain compatible, and the question is, can we come up with a set of strain gradients? Answer is yes. But we have to. That's a part of the theory. There is only a limited set of deformation gradients which are here, but they are not only those which are known in the literature, which can be calculated using the Bhattacharya approach from the lattice parameters, but they are those plus some other created by slip. And they have to fulfill the same condition. They have to fulfill this incompatibility, this m times b.
What are the jump conditions you are following? Because that jump condition which is detailed in the book, like they are following the deformation gradients there. Deformation gradients is multiplied with the slip vector and the normal to that.
No, they have to fulfill it. They have to fulfill it. So the set is broader. It is not only tools proposed in current state-of-the-art model, but it's broader. But what are they? We have to propose. Yeah? So we are working on that. No, but it's not yet published.
And what are the other assumptions you are following in this model?
No other assumptions. I probably said everything. That's all what I said. Yeah, I mean there are no other assumptions. Yeah.
As well as the experiment you were explaining between space versus temperature. So what are the methods you are following for that experiment? Sigma versus theta.
Which one?
The previous one, I guess.
Okay, I don't remember. Okay, I just want to check whether I forgot something. No, I'm at this is the end. Okay. But
Go to the previous slide.
which one?
Yeah, I have to. Yeah, previous one. Yeah, okay. Yeah, here, this one. So you said that you perform an experiment to
No.
display sigma versus theta.
Well, okay. This is about. I didn't discuss this much in the detail, but in order to understand the like a couplet plasticity and transformation, we don't need this. Okay, we don't know how to introduce these quinks, but of course they are here, yeah. But what we have to explain is this. This is the temperature. This is stress, and now we are heating under stress. And in this moment, the martensite is the oriented martensite is changing to plastically deformed austenite. But I need to show the experimental data to explain this to you. Yeah? Without showing the data, it would be this is difficult. But because I consider it very important, and we spent a lot of time to analyze this. This happens during when you are heating under constraint. So yesterday, when we prepared the shape memory spring, we put the spring on the mandrel and put it into the furnace. And when you put it into the furnace, what happens? You are heating, you reach this maximum stress, and you have. So it happens during the shape setting. I would like you to go with you through the way of thinking when we try to understand the processes which occur during the shape setting, and this is in the next talk.